Let me switch you to the world of high field physics, high power lasers, and I would like to start from introductory from the Nobel Prize 2018 for Gerard Mourou and Donna Strickland, who invented so-called CPA, short pulse amplification method, or just short pulse amplification. This concept pushed the laser field or laser power orders of magnitude, and initial idea was published in 1985. And the idea shown on this picture, the whole short pulse laser, or if you would like to get a high power, we need high energy and short pulse. No other way. Energy is always limited, and but the way to short pulse is most important route. But the problem is that there's no problem to generate a very short pulse up to a few or even one optical cycle, which is a 3 femtosecond. And in this case, for femtosecond pulse, 1 joule energy, which is quite moderate, gives you a huge power of petawatt level or multi-petawatt. So there is no problem to generate the pulse, but this pulse is quite small energy. There is no problem to amplify this pulse in laser amplifiers. But the problem is when pulse became very high due to amplification, it kills, destroy optical amplifier itself. So any material which can be used for amplification, no way to amplify the light without medium. But any material damaged by the light itself, just because the light, powerful light, just ionized atoms, molecules, and free electron accelerate in the optical field and destroyed materials called optical damage. So the idea was to stretch pulse in time order of magnitude, which reduce the peak intensity, of course, then amplify it to up to high energy, keeping this level is quite moderate, and after that compress pulse to initial duration to increase peak power. And the trick here is that compressor does not require a medium. Compressor might be made completely on reflective device, reflective grating and diffraction grating, and I will talk about it in this talk. So this technique is called short pulse amplification, which because to stretch the pulse, we have to delay different frequency for different time, and it looks like a gamma for me, but this term chop comes from the microwave science from radar technology. Just to mention that such kind of pulse, short pulse, comes not only in laser field, but this picture is a signal of gravitational wave observer, which was the next another Nobel Prize, and you can see this is the signal of the gravitation wave, and it looks exactly the same, long frequency. First and high frequency and of the pulse. So using this trick, we can increase the, and we can increase the peak power without damage threshold of the amplifier. But of course, compressor itself also is limited but this limit is quite high, and now we are fighting with this limit. Not limitation come from the amplifier, but limitation come from compressor. To compress the pulse, we use many dispersive elements which induced different delay for different wavelengths, but for high energy, high peak power, there is no actually alternative to the deflection grating, because this is only element which avoid propagation beam inside the material. The grating technology is quite impressive. Has very impressive progress during last 10 years, and you can see meter scale diffraction grating on the picture. Now even 2 meter grating is under production, and this very sophisticated technology with a few hundred, actually 12 or 1700 lines per millimeter, with perfect surface of the grating, and it's 92% reflectivity. Oops. Okay, and well, the principle is very simple. It's a basic for grating compressor. You see for grating, and even by naked eye, you can see that the delay for red wavelengths is much higher than the delay for blue wavelengths, and that allow us to compress the pulse. The same idea used to stretch the pulse, which calls the device called stretcher, but with opposite sign of dispersion. So this is a simple compressor. Was actually invented not by Gerard Moreau. It was invented by Edmund Pressey in 1969, which is almost 20 years before Gerard Moreau published. Gerard Moreau and Donald Stichel published a paper, and it is. I was 4 years old, and this paper is published. And until recently, this compressor, Tracy compressor, for grating compressor, all grating parallel, grating parallel to each other. This grating is anti-parallel, the same groove density, the same angle of incidence, so completely symmetric for grating compressor, which provide combining all frequency in the same line, but induce dispersion which we can control. Okay, this is the picture from the Nobel Prize paper, and you can see this grating compressor, 2 gratings and mirrors which use the same grating second times, but the main idea of Gerard Moreau and Donald Stichel was not compressor, but using amplifier to put between stretcher and compressor. Okay, I skip maybe details and coming to a fresh result. The general concepts of 99.9% of high power femtosecond laser is here. So we start from master oscillator with the stretcher, with amplifier, compressor, like here. And we use 2 special devices. One of them is adaptive optics, adaptive mirror, to fix the wave plane, to make the wavefront, plane, because of course our goal not to get a power, but our goal to focus the beam in the small size and reach a high field, high intensity, and which the record of intensity now is around 10 to the 23 watts per square centimeter, which is still a few orders of magnitude lower than Schwinger limit, but still a lot of new physics is behind this intensity. So we don't actually care about power. We need to focus the beam, and for this case we use adaptive mirror, which can adapt the surface, just mechanically adapt surface opposite side of the wavefront of the beam. So we can control the phase in space. Another device which called Dazzler, acoustic device which can control the space in time or in omega domain. Because we don't have many way to change dispersion in this setup. We can, of course, increase the distance between grating and angle a little bit, but much more efficient to use an inline device put in the very beginning of this chain with very small power, so not joules, but microjoules or even nanojoules. It's a linear device, and we can control the phase not in space but in time, more or less induce in the laser pulse the phase, more or less arbitrary phase which we would like to, in our goal to compress our pulse in time to Fourier limit. So we compress our pulse in time using Dazzler. We compress our pulse in space using adaptive optics, but we cannot control space-time coupling using this device because adaptive mirror doesn't know about omega and doesn't know about coordinates. Well, and oops, okay, couple of years ago, two different kind of compressor was proposed based on this fog grating compressor, but modified in two directions. The first direction is this title is not seen. It's asymmetric compressor. So it's the same fog grating, two pairs, but you see that pairs is different to each other. Different distance between grating, different angles, different groove density, actually arbitrary. So grating in each pair are identical, but pair is not identical. It's a completely counterintuitive approach suggested by scientists from Shanghai Institute of Optical Fine Mechanics, leads to such kind of strange beam on the output. In the center of the beam, you will see the all frequency, but red frequency and blue frequency shifted in the space, in vertical, horizontal direction, or even in arbitrary case, in diagonal. So it looks very strange and unwanted for practical application on the first glance. But in reality, it gives us a very useful impact. I will tell you a little bit later. And as for beam focusing, if we put focal length here and see what happens in focal point, we will see that this strange beam, where different frequency come in different place, gives you a focal intensity exactly the same like a perfect beam, which is not shown here, but in general case. So we lose nothing in focal point, intensity is the same. But due to the different frequency come in different space, it's smooth in space on the grating, we can reduce the intensity fluctuation which destroyed our grating and hence increase the laser power. So we can control this asymmetry in. So okay, it's for standard compressor. You see again, it's the same. All frequencies are the same in space, but we can control it in any direction, vertical, horizontal. nothing changed. Okay. And if we combine it all together, we can put some hierarchical. So this is a plane compressor, tracy, or literal compressor, and this is symmetric, asymmetric compressor, and even we can use a two grating compressor, like a final step of asymmetry, where the second part doesn't use at all. And in basic case, the compressor is basic general case is here. It takes 8 parameters, 3 angles, and distance between gratings for each pair. And from this case, we can reduce to any compressor in the simple way. Simple is just basic symmetric basic compressor is only 3 parameters, 2 angles and distance between gratings. So we can do all our math for general case and see what happened in the final formula. So what we can use, we can use a very simple, mathematically very simple approach, which allowed us to make all math analytically. We go to the Fourier domain, Fourier omega k vector, and we use the simple equation, which because the beam passes through the two gratings, it of course keep omega kx and ky the same, and only phase exponential is come here, and we can use the well-known equation for this space, and it allows to calculate all this stuff. And what we can, as I already told, just from this simple equation, we can conclude that intensity of the focal beam point will be the same independently of symmetry of or asymmetry of the compressor and so on. Okay, the first equation is out of screen, but it was on the previous slide. We can use this equation for phase C, psi, 1 and 2 for second and first and second pair equation. This one is the diffraction grating formula connecting incident and output angles in general case where the k vector is not for x and y is arbitrary. And we can do very simple math just to put the second derivation of this phase to obtain all we need. I skip all the math, but I would like to stop on this very simple picture, which to explain physically why the beam clean up from the noise in the grating in the asymmetric compressor. The simple estimation is, I already told, is just beam smoothing through in space. But more physical picture is here. This picture is even not for grating compressor, just for free space propagation, but it's very important and for understanding. So if we start from this, let me say z equal to 0 plane, we have main beam, which is shown in blue, and phase, which is shown in red, or in noise, which is shown in red, in space and in time. In space, the noise is, of course, much smaller than the beam, but the scale of the noise are arbitrary. All scales are inside the noise. In space domain, usually, of course, again, noise is much smaller than the main beam, but in time domain, it's more or less the same like main pulse. The simple model is just if you start from the even perfect beam, but after reflection of the any mirror, due to mirror surface is not flat, looks like this one. The scale is sub wavelengths, it may be tens or even 100 nanometers, 100 wavelengths, but it still is. So we have the same in time, of course, after mirror, but in space we have such kind of noise. After propagation, even in free space, what we have, of course, we have diffraction in space domain, and this red noise contains full spectrum of K vector, and due to diffraction, this such K vector sooner or later removed from the beam, from the aperture of the beam, and does not impact on the beam quality. I mean this part of the beam. Of course, it depends on this angle and distance, but it works. In any case, it works as a special filter. For femtosecond pulse, it is in space. It's even for CW radiation. For femtosecond pulse, we have a second effect. Due to noise propagate through the angle, it's delayed through the main pulse, just because the distance is higher than the distance. Of course, its effect quite small for small angles, but it is, and all we need to remove noise from the beam to kill interference of the noise and beam of the main pulse and noise. We need just delay the noise to the pulse duration. Pulse duration is a femtosecond, a 10th femtosecond, which means that we need 10 microns to delay, not so much. It's very powerful effect, and if this noise delayed, okay, it does not interfere with the main beam, and it gives us opportunity to clean the beam. The same story takes place in compressor, because compressor contains free space propagation, of course. But in addition to this effect, we can accelerate, we can push this effect by using this asymmetric compressor, which smooths the different frequency in the beam, as I showed you in previous pictures. And this allows us to get this cleaning very efficient, but not for very long distance and very small angles, very high angles, but even for pretty small angles and distance, which is reasonable. And so this slide again, just to emphasize what happened, what we see in this picture, we see fluence. Blue is a perfect plane wave. Black is real fluence with noise. It's sigma. And what we can see, we would like to reduce this fluctuation to increase the laser power without breaking of the damage threshold. So as much as we reduce the sigma, as we can increase the fluctuation, the energy of the beam without damage threshold. Okay, again, I can skip the math. I just show that all this stuff might be done analytically, and we get this simple equation. RMS of the output beam out of compressor, we normalized to reference case. Reference case is a symmetric tracy compressor, which used in 99% of lasers now so far. And you can see that this ratio depends on the one parameter, which coincides all stuff, bandwidth, asymmetry of compressor, wavelength, and scale, special scale of the noise. And this graph show, last slide actually, this graph shows just an example how we can reduce this ratio reduce the noise compared to the reference case. We will send a basic compressor just using a degree. Gamma is the angle out of plane angle. So we just use not 0 angle but 1 degree angle, and in case of 1 millimeter scale noise, we can reduce in the order of magnitude using just 1 degree angle instead of normal incident. Of course, if the scale of the noise much higher, for example 10 nanometer, result is not so optimistic. We need 4 or even more angle, which contradicts nothing, but break geometry a little bit. But in any case, we can reduce this noise by factor of 5 or even more with very small deviation of the angle, and this effect was demonstrated in experiment. So, but I would like to conclude. What we have studied, we studied the 2 ways to upgrade Tracy compressor, which used 60 years, almost 60 years. 2 ways we discuss in beam smoothing, so asymmetric compressor and out of plane literal compressor, or the combination. And what we reached, we reached a reduction of the noise, special noise, and the output of a compressor, which allows us to save grating and focusing optics after grating as well, and increase the laser power without damage threshold, without overcoming damage threshold. And also, out of plane compressor allows us another benefit to save space on the grating, which means we can expand our beam and use a larger beam. And if we are limited by the damage threshold by typically 100 millijoules, 100 millijoules per square centimeter, if we increase the beam diameter, we can increase the energy, which is quite important for high power lasers. Thank you for your attention.